Welcome to this coding walkthrough. Today, we'll tackle LeetCode problem number 35, Search Insert Position. This is a fundamental problem that tests your understanding of binary search and array manipulation. We'll break it down step by step to help you master the approach. Let's get started. In this problem, we are tasked with finding the position to insert a target value into a sorted array of distinct integers. The goal is to ensure that the array remains sorted after the insertion. If the target value already exists in the array, we simply return its current index. However, if it doesn't exist, we need to determine the index where it would fit while maintaining the sorted order. The solution must be efficient, with a time complexity of O log n, which suggests that we should aim for a binary search-based approach rather than a linear one. The input consists of the array nums, which is sorted in strictly increasing order, and the integer target, which we need to locate or insert. The output is a single integer that represents the required index for the target. Let's look at an example to understand this better. Suppose the input is nums equals 1, 3, 5, 6, and target equals 5. The output in this case is 2 because the target value 5 already exists in the array, and its index is 2. In another scenario, if the input is nums equals 1, 3, 5, 6, and target equals 2, the situation changes slightly. Since the target value 2 is not present in the array, we need to find the position where it would fit while keeping the array sorted. In the case where the target is 2, the output is 1. Here's why: the value 2 would fit between 1 and 3 in the array. Inserting it at index 1 ensures that the array remains sorted. Now, consider another example where the input is nums equals 1, 3, 5, 6, and target equals 7. The output here is 4 because the target value 7 is greater than all the elements in the array, so it would be placed at the end. This means it should be inserted at index 4 to maintain the order. Another example helps illustrate a different scenario. If the input is nums equals 1, 3, 5, 6, and target equals 0, the output is 0. This is because the target value 0 is smaller than all the elements in the array. Therefore, it would come before the first element, and the appropriate index for insertion is 0. These examples demonstrate how the problem handles targets that are smaller, larger, or in between the existing array elements. The constraints of the problem ensure that the array is always sorted and contains distinct integers, which simplifies the insertion logic. The problem also specifies a few important constraints and edge cases to consider. For example, the target value can range from -10⁻4 to 10⁻4, and the array size can be as large as 10⁻4. Edge cases include scenarios where the target is smaller than all elements in the array, larger than all elements, or equal to the smallest or largest element. Additionally, we should account for cases where the array contains only one element. By understanding these constraints and edge cases, we can ensure that our solution is robust and handles all possible inputs correctly. To solve the problem of finding the correct index for a target value in a sorted array of distinct integers, we can explore multiple approaches. The most straightforward method is the brute force approach. Here, we simply iterate through the array and identify the first index where the element is greater than or equal to the target. If no such element exists, the target should be placed at the end of the array. This process involves traversing the array from left to right, comparing each element with the target, and returning the appropriate index. While this method is simple and requires no additional space, it has a time complexity of O (n), which can become inefficient for large arrays. Given that the array is sorted, we can leverage this property to develop a faster solution, which leads us to consider binary search as an optimized alternative. A more efficient approach to solving this problem is to use binary search. This method takes advantage of the array's sorted nature by employing a divide-and-conquer strategy to systematically narrow the search space. To implement binary search, we start by initializing two pointers, one at the beginning and the other at the end of the array. We then repeatedly calculate the middle index and compare its value with the target. If the middle value matches the target, we return its index. If the middle value is less than the target, we shift the left pointer to exclude the lower half of the array. Conversely, if the middle value is greater, we adjust the right pointer to exclude the upper half. This process continues until the pointers converge, at which point the left pointer will indicate the correct insertion index. The binary search approach is highly efficient, with a time complexity of O log n, as the search space is halved at each step. Additionally, it requires no extra space, making it both time and space efficient. While this method may require a deeper understanding of binary search mechanics, it is far more suitable for large arrays compared to brute force. Another variation of binary search is the recursive implementation. This approach achieves the same time complexity of O log n, but differs in its use of recursion instead of iteration. In the recursive binary search, the function repeatedly calls itself with updated boundaries until the target index is found or the search space is exhausted. While this method can be more intuitive for those comfortable with recursion, it comes with a trade-off. Additional stack space is required for each recursive call, leading to a space complexity of O log n. This means that for very large arrays, the recursive approach risks stack overflow, making it less practical in certain scenarios. After evaluating the options, we selected the iterative binary search as the preferred strategy. It combines the efficiency of binary search with the practicality of avoiding recursion, making it a robust solution that scales well for large inputs. The key insight here is the realization that the sorted nature of the array allows us to achieve logarithmic time complexity, which is optimal for this problem. To summarize, the key observations that shaped our approach are centered on the properties of the input array. The fact that the array is sorted allows us to use binary search, ensuring an efficient logarithmic time complexity. By opting for the iterative version of binary search, we avoid potential issues like stack overflow that can arise with recursion, while still maintaining the same level of efficiency. In conclusion, the iterative binary search stands out as the most practical and efficient approach to solving the search insert position problem. It leverages the guarantees provided by the problem constraints to deliver an optimal solution. In this problem, we are tasked with finding the index where a target value should be inserted into a sorted array to maintain its order. The array contains distinct integers, and the goal is to determine this position efficiently. To achieve this, we use the binary search algorithm, which is well suited for sorted arrays. We start by initializing two pointers, left, which is set to the beginning of the array at index 0, and right, set to the end of the array at index len, nums, 1. These two pointers define the current search space. The algorithm then operates within a binary search loop. While the left pointer is less than or equal to the right pointer, we calculate the middle index using the formula mid equals left plus, right left, // 2. This calculation prevents potential overflow issues that could arise from directly summing left and right. Once the middle index is determined, we compare the value at nums, mid, with the target. If they are equal, we've found the target's location and can return mid. If the middle value is less than the target, it means the target must lie in the right half of the array, so we adjust the search space by updating left to mid plus 1. On the other hand, if the value at nums, mid, is greater than the target must lie in the left half of the array. In this case, we narrow the search space by updating right to mid 1. Now, if the binary search loop completes without finding the target, the left pointer will indicate the correct position where the target should be inserted. This is because left always points to the smallest index where the target value could fit while maintaining the array's sorted order. Binary search is particularly effective here because it halves the search space at each step, giving us a time complexity of O log n. This efficiency is the key reason for using binary search in this problem. Additionally, returning the left pointer ensures correctness in all scenarios. If the target value is smaller than all elements in the array, left will remain at 0. And if it's larger than all elements, left will equal the length of the array, pointing to the correct insertion at the end. This approach also handles edge cases, such as an empty array, where 0 is the only valid insertion point, or scenarios where the target is smaller or larger than all elements. If the target value is already present in the array, the binary search will find its current position and return the corresponding index. This ensures that no duplicate elements are added to the array. The algorithm itself is straightforward in terms of data structures. We only use the input array nums and two pointers, left and right, to track the current search space. This means the space complexity of the solution is O1, since no additional data structures are required. The time complexity, as mentioned earlier, is O log n, due to the efficient halving of the search space. Let's walk through a concrete example to better understand how this works. Consider the array nums equals 1, 3, 5, 6, and the target value 5. We start by initializing left at 0 and right at 3. Calculating the middle index gives us mid equals 1. The value at nums, 1, is 3, which is less than 5. Therefore, we update left to mid plus 1, which is 2. Recalculating the middle index gives mid equals 2, where nums, 2, equals 5. Since we found the target, we return the index 2 as the result. Now, let's consider a different target value, such as 2. With the same array nums equals 1, 3, 5, 6, we initialize left at 0 and right at 3. Calculating the middle index gives mid equals 1. The value at nums, 1, is 3, which is greater than 2. This means the target must be in the left half of the array, so we update right to mid 1, which is 0. Next, we recalculate the middle index with the updated pointers. Now, mid equals 0, and nums, 0, is 1, which is less than 2. This means the target must lie in the right half, so we update left to mid plus 1, which is 1. At this point, the left pointer exceeds the right pointer, causing the loop to exit. The value of left, which is 1, represents the correct insertion point for the target. This ensures that the target value would fit in the array while maintaining the sorted order. The corresponding Python code implementation reflects these steps. It uses a straightforward binary search loop, updating the left and right pointers based on comparisons between nums, mid, and the target. If the target is found, the index is returned immediately. Otherwise, the final value of left is returned after the loop ends. To summarize, this algorithm is an elegant application of binary search, achieving optimal performance with a time complexity of O log n. By leveraging the properties of a sorted array, it minimizes unnecessary computations while maintaining a simple and efficient implementation. The algorithm handles all edge cases seamlessly, including empty arrays, targets smaller or larger than all elements, and scenarios where the target is already present. With a space complexity of O(1), it is also highly memory efficient. This combination of simplicity, efficiency, and robustness makes it a powerful solution to the search-insert position problem. This implementation solves LeetCode problem number 35, search-insert position, using a binary search approach. The goal is to find the position where the target value fits in a sorted list, either as an existing element's index or as the proper place for insertion. The function begins by initializing two pointers, left and right, which define the search boundaries. Initially, left is set to 0, and right is set to the last index of the list, len, nums, 1. Next, we enter a while loop that continues as long as left is less than or equal to right. This ensures that the search space is not empty. Inside the loop, we calculate the middle index mid using integer division, left plus right, //2. If the middle element nums, mid, is equal to the target value, we immediately return mid, as we have found the desired index. If nums, mid, is less than the target, we adjust the left pointer to mid plus 1 to search the right half of the list. Conversely, if nums, mid, is greater than the target, we adjust the right pointer to mid 1 to search the left half. If the loop terminates without finding the target, the left pointer will point to the correct insert position for the target. This is because left tracks the smallest index where the target could fit while maintaining the sorted order of the list. Thus, we return left as the final result. This solution operates in O log n time complexity, making it efficient for large input sizes. It handles edge cases such as an empty list, the target being smaller than all elements, or larger than all elements seamlessly due to the binary search logic. This is the Java implementation of LeetCode problem number 35, search-insert position. The logic mirrors the Python solution, using a binary search approach to find the index of the target value or its appropriate insertion position. Key differences include Java's explicit type declarations and the use of int arrays. The while loop efficiently narrows the search range, and the calculated left index is returned if the target is not found. In this example, we're given the sorted array nums equals 1, 3, 5, 6, and the target value 5. The goal is to find the index where the target exists. We start by initializing two pointers, left at 0 and right at 3, which is the last index of the array. Next, we calculate the midpoint using the formula, left plus right, //2. Here, it evaluates to 0 plus 3 // 2 equals 1, so mid points to index 1. Checking the value at nums 1, we find it equals 3. Since 3 is less than the target 5, we adjust the search range by moving the left pointer to mid plus 1, which now becomes 2. Recalculating the midpoint after this update, we get 2 plus 3 // 2 equals 2, so mid is now 2. Looking at nums 2, we find it equals 5, which matches the target. Therefore, we return the index 2 as the result. Now, consider the case where the target is not present in the array. Here, the input is nums equals 1, 3, 5, 6, and the target is 7. Again, we initialize left at 0 and right at 3. Calculating the first midpoint, we get 0 plus 3 // 2 equals 1, so mid is 1. The value at nums 1 is 3, which is less than the target 7. To narrow the search range, we move the left pointer to mid plus 1, which is now 2. Recomputing the midpoint gives 2 plus 3 // 2 equals 2, so mid points to index 2. Checking nums 2, we find it equals 5, which is still less than 7. Again, we move the left pointer to mid plus 1, updating it to 3. Recalculating the midpoint one more time, we get 3 plus 3 // 2 equals 3, so mid is 3. The value at nums 3 is 6, which is still less than 7, so we move left to mid plus 1, making it 4. At this point, left is greater than right, which ends the loop. The left pointer now points to position 4, indicating that the target should be inserted at the end of the array. Thus, the output is 4. Here, we explore another scenario where the target is not in the array, but this time it needs to be inserted at the beginning. Given nums equals 1, 3, 5, 6, and target equals 0, we start with left at 0 and right at 3. Calculating the midpoint, we get 0 plus 3 // 2 equals 1, so mid is 1. Checking nums 1, we find it equals 3, which is greater than the target 0. To adjust the search range, we move the right pointer to mid 1, updating it to 0. Recomputing the midpoint with this new range gives 0 plus 0 // 2 equals 0, so mid is now 0. The value at nums 0 is 1, which is still greater than 0. This time, we move the right pointer to mid 1 again, setting it to minus 1. With left now greater than right, the loop ends. The left pointer, currently at position 0, indicates that the target should be inserted at the beginning of the array. Therefore, the output is 0. The key takeaway from this algorithm is its use of binary search to efficiently locate the target or determine its insertion point. By repeatedly having the search space, the algorithm achieves a time complexity of O log n, making it highly efficient for large arrays. When the target exists in the array, the algorithm directly returns its index. However, if the target is not found, the left pointer accurately identifies where the target should be inserted to maintain the sorted order. The dynamic adjustment of the left and right pointers ensures that all scenarios, including edge cases like inserting at the beginning or end of the array, are handled seamlessly. This iterative narrowing of the search space allows the algorithm to quickly and reliably solve the problem. Here, we analyze the time complexity of the algorithm, which is based on the binary search approach. The size of the input array is denoted as n. Binary search works by repeatedly dividing the search space in half. In each iteration, it calculates the middle index and compares the value at that index with the target. This halving process significantly reduces the search space. The number of iterations required in the worst case is directly proportional to the number of times we can divide n by 2 until we're left with a single element. Mathematically, this is represented as log 2, n. Furthermore, each iteration involves computing the middle index and performing a comparison, both of which are constant time operations, or O(1). When you multiply the O log n iterations by the constant work per iteration, the overall time complexity of the algorithm becomes O log n, making it highly efficient. Now, let us break this down into specific scenarios. In the best case, the target is located at the middle index during the very first iteration, requiring just one comparison, which translates to a time complexity of O(1). On average, the search space reduces logarithmically, resulting in O log n. The worst case occurs when the target is not present in the array, requiring the algorithm to perform all possible iterations until the search space is reduced to a single element. Even in this scenario, the time complexity remains O log n. Moving on to space complexity, the algorithm operates in place, meaning it does not use any additional data structures. The input array is used as is, without copying or modifying it, so no extra space is allocated. The algorithm uses 3 integer variables, left, right, and mid, which occupy constant space, or O1. Since the implementation is iterative, there are no recursive calls, and thus no memory overhead from a call stack. As a result, the total space complexity of this algorithm is O1, or constant space. To better understand the efficiency of this approach, let's compare it with a brute force method. A brute force approach would involve iterating through the entire array to locate the position for the target. In the worst case, this requires n comparisons, leading to a time complexity of O(n). The binary search approach, on the other hand, dramatically improves this by reducing the time complexity to O log n, due to its halving of the search space. Both methods share the same space complexity of O1, since neither requires additional data structures. What makes binary search optimal is its ability to exploit the sorted nature of the array, resulting in exponentially fewer steps compared to linear search. This logarithmic time complexity is particularly advantageous as the size of the input grows. Finally, let's solidify the reasoning behind the big O analysis. The total number of iterations in binary search depends on how many times the search space can be halved, which is mathematically proportional to log 2n. Each iteration involves simple operations like calculating the middle index and performing a comparison, all of which are constant time operations, or O1. When we combine these, the overall time complexity becomes O log n, asterisk O1 equals O log n. Regarding space complexity, the algorithm only uses a few variables and does not allocate extra memory, resulting in constant space usage, or O1. In conclusion, this binary search algorithm achieves an impressive time complexity of O log n and a space complexity of O1. Its efficiency makes it an excellent choice for searching in sorted arrays, significantly outperforming brute force methods in terms of speed as the input size increases. When solving the search insert position problem, there are a few common mistakes to watch out for. First, not accounting for edge cases can lead to runtime errors or incorrect outputs. For example, if the array is empty or the target is smaller than the smallest element or larger than the largest element, the algorithm must handle these scenarios gracefully. A common mistake here is returning -1 or encountering an unhandled exception. Next, using a linear search instead of binary search is another pitfall. While it might work for small inputs, it results in O(n) complexity, which is inefficient compared to the O log n complexity of binary search. Another issue arises from incorrect midpoint calculations in binary search. Using the formula mid equals low plus high /2 can cause integer overflow in languages like Java or C++ for large values of low and high. Instead, the safer calculation is mid equals low plus high low /2. Finally, watch out for off by 1 errors when adjusting the low or high pointers. For instance, setting high equals mid instead of high equals mid 1 can lead to infinite loops or incorrect results. These mistakes can be subtle but significantly impact the algorithm's correctness. Another common mistake is not returning the correct insertion index. Misinterpreting the results of binary search can lead to returning the wrong index where the target should be placed. Always ensure the algorithm accurately determines the position where the target fits in the sorted order, even if it's not present in the array. Now, in an interview setting, this problem is a great opportunity to demonstrate your understanding of binary search and its variations. Binary search is a fundamental algorithm often tested in interviews, so it's important to ensure your implementation is both efficient and free of bugs. Additionally, be mindful of edge cases, such as when the array has only one element or when the target is outside the array's range. Clear communication is also key during interviews. Explain why binary search is the optimal approach, and highlight its time complexity of O log n. Lastly, emphasize the real-world relevance of this problem. For example, it's commonly used in applications like searching for positions in sorted lists or implementing efficient lookup systems. This problem is closely related to several other LeetCode problems, which can help reinforce your understanding of binary search. For instance, LeetCode 704, binary search, is a more straightforward version where you simply find the index of an element in a sorted array. Another example is LeetCode 278, first bad version, where binary search is used to find the first occurrence of a bad version in a sequence. LeetCode 744, find smallest letter greater than target, adds a twist by searching for the smallest element greater than a target in a circular sorted list. Lastly, LeetCode 852, peak index in a mountain array, demonstrates how binary search can be applied in more complex scenarios, such as finding the peak of a mountain array. Exploring these related problems can deepen your understanding and prepare you for variations of binary search in interviews. There are also alternative approaches to solving this problem, though each comes with its trade-offs. Linear search, for example, is very simple to implement but has a time complexity of O(n), making it unsuitable for large input sizes. This approach might only be appropriate for small arrays or when binary search isn't explicitly required. Another option is recursive binary search, which uses recursion instead of iteration. However, it carries the risk of stack overflow for very large input sizes due to limited recursion depth. This approach might be preferred in scenarios where recursion is specifically requested. Finally, some developers opt for custom iterative methods, such as maintaining a running pointer to find the insertion position. While this approach can work, it is generally less efficient and undermines the purpose of using binary search. Understanding these alternatives can help you make informed decisions based on the problem's constraints and requirements. Great job! To wrap up, we solved LeetCode problem number 35 using binary search, achieving an efficient solution. Remember the importance of edge cases and using the right tools for sorted data. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!